Now that we know that some of these problems are, we call them hard, so I think it's a good time to discuss about how do we classify them. And so something that we would use a lot in cryptography is what we call hardness assumption. So the factorization problem that we just talked about in the before the break time was one of those algorithms that we do not know if we can actually solve it in a polynomial time right now. The algorithm that we came up to go all the way to try many different primes until we find a perfect divisor for it is some problem that we call it hard problem or hard assumption. The reason that it is an assumption and is not, like, for example, NP hard or NP complete problem is that we haven't proved yet if there is an algorithm that we can solve it in polynomial time. And on the other side, we can also prove that there is no algorithm to solve, to factor integer in a polynomial time. So we don't have the answer for both sides. There's no algorithm we know how to do it, and we can't even prove if there would be no polynomial time algorithm ever to solve such a problem. So these problems are, you can imagine, that are somewhat up on the sky. Nobody can prove them, nobody can disprove them. But these problems are standing out there for many years, and many scientists, they try to solve this problem to show them if they are easy or difficult problems, and they couldn't. And it is more opinions towards the fact that they are actually definitely a hard problem and we can't solve them. So that's why we want to be very careful, and we want to use the notation of hardness assumption, or like factorization. We don't have actual proof that it is really NP or NP complete problem, but we just know that it is a hard assumption. We would be able to create some crypto system such as RSA on the top of it, but we assume that as long as factorization is a hard assumption, then nobody should be able to break RSA. So that is something that we can tell. So I just brought this slide to the slides here to make this make you to really differentiate between a long-standing problem that is proven, for example, to be NP complete or NP hard, and some assumption that is just an assumption and we don't have any proof for it. So this is very important word, and we have to be very careful about it. Another problem that we have is a discrete logarithm. This problem is also not polynomial time solvable. So let's say what is this problem and what is it in the first place. So given that we have a generator, we have a prime p and a y, and then you want to compute this equation that is literally a logarithm of some value, but since we do it mod p, the name would change to differentiate this from the real logarithm value function that we know in practice. Because of this mod p, the name changed to discrete logarithm. Discrete because it's basically integers. There's no fractal values that this function would return. So the story is that we know that in some sort of computation, we can find y to be congruent to g to the power sum x mod p. Okay. So G is a generator, is a very special element that we will talk about it in future. You get the G, you raise it to some power x, and then you compute mod p, you land to some other integer y. And then the question is that given this p, G, and y, can you find this x for me? And that is known to be a discrete logarithm problem, because literally you can write this equation as x equals to log of y mod base g mod p, right? So that is why it gets the name of logarithm, discrete logarithm. So so let's see why is it difficult. So let's again write our pseudocode, or famous pseudocode. So remember that this is the different group that what we have mod n in. Let me go back. In RSA, if you remember, we always did a computation based on mod n, where n is actually a composite number, p times q. But now we are talking about a different group that is mod p. And this group is a little bit different than mod n. And it has a little bit higher security, even though p is much smaller than n. And roughly we say that p can be only 512 bits. And if we form a group of a smaller p, then we can have a security of some larger RSA bits. So this is an equivalent problem for that RSA. So again, since we don't have a polynomial algorithm to solve it, so our brute force algorithm, we can write it as for x equals to 2 to all the way to p minus 1 actually, which is 2 to the power 512 minus 1. we check if y equals to g to the x mod p, and if this is the case, then just return x, and that is the answer that we were looking for, right? So again, as you could see, for this one, it slightly look like that this for loop is smaller than the RSA, but actually this is exactly just like RSA. If we go back for the RSA of 1024 bits, and if you wanted to do factorization, we said that we have to check this many numbers, and as you could see for yourself here, it is almost equal to working on that group with a smaller p is equivalent to working on an RSA with 1024 bits. So this has some advantages in terms of computation and providing the same level of security. So these would be some material that we would discuss about it in the future. So like you see that we switch from some different group of mod n. Now we switch to a different problem that actually can be remain difficult in a smaller group. So this would bring us some advantage for computation, because the same problem, we can represent the integers in this problem with only 512 bits. But for RSA, M, C, message, ciphertext, secret key, and all those stuff, we need at least 1024 bit to represent them, right? So the computation is actually being on modular exponentiation on 1024 bits. And over here, we have the same modular exponentiations, but the values over here are only 512 bits. So you could see that these computations are a little bit faster, at least twice faster than that of the RSA. So it would be interesting to see if we can construct some crypto systems using this problem rather than the RSA problem that we all know about. All right. So this would bring us to a very interesting and important concept in cryptography, and that is reduction. Before I get into this, let me ask you, how many of you have heard about reduction? Maybe you can type yes if you have heard about it. Or how many of you have taken the course called computational complexity? Okay, at least one student. All right. So it looks like that this is a new thing for most of you. So we're gonna spend some time here with many different examples to really understand, because for security proofs, we are going to rely mostly on a new technique that for most of you probably is new technique, called reduction. So in the mathematics, you've learned that you can prove different things with different methods. For example, with induction, for example, with contradiction, and different techniques that you would use. Unfortunately, those ways of proving wouldn't really help us for proving the security of the crypto systems, because we are working on a special groups and a special problems. So we would mostly talk about the different fact, and the fact is reduction. So let's see how does this work. So I try to give you draw a picture so that it becomes easier for everybody to understand. Oh, if my pen works. All right. So suppose that I have a problem called pi. I use a capital pi. And then this problem pi would take an input x. And then, if somebody knows how to solve this problem, it would output some s of x. And suppose that is, the function. Pi is a function. Pi is a problem. And then we have another problem that calls gamma, that this problem would take different inputs. For example, this take y, as input. And then when you solve it, then you get s of y, right? So you have two different problems. They have different inputs, and then they have different outputs. And then what becomes interesting is that you can connect these problems to one another. What do I mean by that is that if I can find some function called f of x, that's, this f would take x and would convert it to y. So take the input from problem pi and convert that into an input for problem gamma. And then once this computation is done, I can find another function g that takes that s of y and convert it into s of x. So it's really meaning that if I want to solve this problem pi, and suppose that there is a solution for this problem gamma, so there is a algorithm A that on input y, it would output s of y. Then it looked like that I can take this algorithm, and by just converting the input and converting this output, I can also solve problem pi. And that becomes interesting because the way that we've just constructed this, I can use this whole thing, like if I can put it in a box, as an algorithm that I call it algorithm B. Right? So let's review it one more time. I have a problem pi that I want to solve it. Pi would take it input x, and the output should be s of x. But unfortunately, I don't have any algorithm to solve pi. We somehow construct this, what we call it reduction, that this reduction would take the input from pi problem with the function f. It will convert it into an input for problem gamma. Gamma, there is an algorithm A that would basically solve gamma. For any y, we pass y to A, and A would be able to solve this problem. And then if you are able to find another function g that takes the output of gamma to the output of pi, then I can use this whole conversion by using f function, a function, and g function. I am able to solve this problem pi that I couldn't solve it before. And therefore, I'm going to use this whole box here, the interaction between these all things over here, as algorithm B. And one thing become interesting, that you see this weird notation over here, that polytime. And it's not really a smaller, but it's a different symbol. So I am only interested, so this would make this one to be, we would denote it as a polytime. So it is interesting that for me that this whole thing is a polynomial time. So if, for example, function f would take time t1 to solve, to output y, and function a is also a polynomial time function that it takes time t2, and g over here that also converts the outputs to one another, it also is t3, such that t1 plus t2 plus t3 is a polynomial time, right? So if t1 is a polynomial time, f can be computed in a polynomial time, a can resolve polynomial time, g also is polynomial time, then I can claim that the order of algorithm B is basically a polynomial time, right? Because the algorithm B is, actually this is the wrong notation. So B is a polytime, right? Or it is T1 plus T2 plus T3, right? So that means that I have found a very good and efficient polynomial time algorithm for solving problem pi that I didn't know how to solve pi in the first place. Okay. So I know this is a bit confusing in the first time. So let me plan out a very interesting problem, and where most of you know how to probably you might have used it sometime. So let's say I want to give you a problem. Before we talk about it, let's discuss it about it over here. So suppose that I want to have an app that when I give a picture to this app, this algorithm, let's say, and then the picture contains some text, and I want the algorithm to speak out or read anything that is inside this picture for me. What is your suggestion? Do you know any algorithm that you just give your text as an input, image input, which is a picture of some text, and then this algorithm can read whatever the text is in this picture? Any opinions? Anyone want to share any opinion? How would you solve this problem? Or do you know any algorithm can read whatever the text is inside a picture? It's okay. Let's see how we can actually solve this. So I'm going to use the same notation, and I want to just make it familiar for you that what we do in a daily life is just nothing by what we do over here. So imagine, suppose I define problem pi to be, read the contents of, I want to solve this problem, but I don't know any algorithm or any library that can do this for me. But I know that there are some libraries that they can extract text from an image, right? So I define gamma to be a problem for extracting text from picture. Okay. So does it start to make sound right to you now? So I have pi here that it takes the input of image, right? And then I have gamma over here that this one will also take the take an input as an image. So the f of x over here, the f function is just like constant, right? You don't need to do anything, just pass it to the pi. And then there is an algorithm A, there is a library A over here, right? So we can use different libraries that are out there. So a library for text extraction, right? There are a bunch of libraries in image processing that we can just use them. And then when you pass this A, the output would be some text, right? That is inside this image, correct? And then once I got that text, I need to change that one to a voice because I was expecting that on input image, I get a voice, right? So what I can do is that I have the text and my G is actually very easy to implement, right? You can use something like Alexa, right? From Amazon, that she would read whatever the text it is there. So in a daily life, we are basically using this reduction a lot. So if I compute the time, T1 is just constant 1, we just don't do anything. And then we have this time for algorithm 2. And also we have some time T3 for Alexa, right? We all know that T2 and T3, we can do it very fast, so they are polynomial time. And therefore, we have found a solution for our problem that we didn't know how to solve it in the first place. Basically, I would say that most of the time that you are writing a piece of code and you would start to you would start to use some library. For example, you want to, let's say, work with files. Well, you add a library for a file, and then you will solve your problem because a part of your problem wants to deal with the files. So you're basically doing reduction all the time, but you just didn't know that the name of or whatever operation you're doing is called reduction because you're relating one problem to another. And solving, if you don't know how to solve your problem, you basically break it down to some other problems that you have the answer. And then at the end, you will somewhat combine the answers, and then which is your function G over here, to build the output that you were expecting for problem pi. So now that this would rhyme a lot better for you, and you are more familiar that, okay, reduction, even though we explained it over here and it sounds like a bit abstract and it's hard to understand, but now I hope that this example over here makes it easier for you to really understand what do we mean by a reduction. And then you would start to wonder, so what does that has to do with security? So we are trying to give you some more examples until we get to the point that you can see for yourself why is it important and what can we do with this. But before we get there, I would like to have a few more examples so that these are also crypto related examples. We have a notation, equation by Lagrange. So it says that it is denoted by capital A for any input A and a prime P. The function would output either +1 or either -1. And there is a notation called quadratic reductivity, but that is not the point of here now, but in case that you just want to know where this comes from. And there are some integers that are less than P that there exists some y, some other integer less than P, such that y to the power 2 is equivalent to A mod P, right? And y is also less than P. So these look like that they are very special numbers, that there exists another number that if you raise that number to the power 2, you get this number A. And if that is the case, this function says that it is a quadratic residue, meaning that the number that there is another number less than P that you compute a square and you get to this number. Or if they're not, then this function would just output -1. This is a very specific function in crypto, and then in future you will start to understand why is it important. But for now, we are just defining what this function means. And then we have also another symbol called Jacobi symbol that also takes the same integers, but instead of an integer and a prime, now it takes an n, which is a composite. And it has the same value that there exists a y such that y to the 2 is equivalent to a mod n. Okay. And here I should say otherwise. So now the point is that we want to connect these problems. But before I do so, let me give you an example over here. So if I compute the Jacobi symbol of 6 and 10, then 6 is a +1. But you may ask why? Because there is a number called 4. If I raise it to the power 2, it would become 6 mod 10. How so? If I raise 4 to the power 2, it becomes 16 mod 10. The remainder to 10 is just 6, right? So the 6 is a Jacobi, the 6 is a quadratic residue mod 10, and this function would output +1. So it turns out that there is a correlation between these two, because this is just Lagrange is working on P, and over here on the Jacobi, we didn't change anything, and the notation is all the same, except that instead of mod P or P over here, we switch to N, which is a composite. And then there is a famous theorem that it shows that if you can decompose N, if you can factor N, and normally for factorization, it is not always a P and Q. Normally it is, some more integers. So we normally denote it by P1 to the power E1 times P2 to the power E2, all the way to Pk to the power Ek, right? Let me give you an example. Let's say N equals to 100. Then I can decompose this one to be, these Pi's are prime. So such that Pi's are prime. So I can decompose 10 as 2 to the power 2 times 5 to the power 2. Also, 2 to the power 2 is 4. 5 to the power 2 is 25. 25 times 4 is 100, right? 2 and 5 are prime numbers. So therefore, this is the correct decomposition or factorization of this integer n. So the same theorem says that if you have the factorization of n, then you can compute the Jacobi symbol of any number based on the composite number n over here to be L of a and p1 to the power e1 times L of a and p2 to the power e2 all the way to L of a and pk to the power ek. All right, so it looks like that there is a way to connect these two problems. So let's do the reduction for it and see how it works. So let me change the color. So now we have pi. This pi is computing the Jacobi symbol, right? J, A, and N that I'm looking for. But we know that we can solve pi, which is pi is factor n. Okay. So the input format of this problem is A and N. I can, the factorization would just take an integer n. So we just we drop one of them. So the f of f over here is just very simple. Where input A and N, f would return n. And if there is algorithm A that can do factorization, that, with given this problem, it would just output the factorization. which is P1, P2 all the way to PK, and E1, E2 all the way to EK, then I can solve this problem by computing this Jn function. So the G is equal to L of A and P1 to the power E1 times all the way to L of AK, I'm sorry, A and P to the power EK. And done. Then this would be our result, right? So we have basically built this function together. I didn't know how to compute Jacobi symbol, but now that I know that based on this theorem, I basically just need the result of this theorem, that if I know the factorization of this n, then I should be able to use Lagrange function over here, which is easily computable in a sublinear logarithm order, and then I am able to compute the Jacobi symbol and see that I relate one problem to another problem, right? So now I can start to make ideas over here so that you could see that well, I have connected this problem to the factorization. I know that factorization is a hard problem. So A is certainly not a polynomial time. So I know T1 over here is just the order is 1, and T3 is also polynomial, but T2 I do not know, because T2 is whatever it is. I know that it is a hard assumption, and there is no polynomial time algorithm that we are aware of that on input n, I can get the factorization of n. And you see that we are not able to basically use this to compute Jn, but here I'm making a different assumption or different conclusion, that maybe Jan or Jacobi symbol is also computing the Jacobi symbol is as hard as factoring n, right? So as long as somebody can factor a, then I am able to compute the Jacobi symbol. And if somebody can compute the Jacobi symbol, supposing that this is the only way and there's no other way, then it implies that the Jacobi symbol is also hard. Assumption is hard to compute because, as a subroutine, I have to find the factorization, and that is something that I know that I can't do that in polynomial time. So this is a different usage. Let's see another, actually the last example. So we are talking about graph coloring. Maybe you guys have seen this algorithm out there in algorithms course. I feel like somebody's mic is on. If you guys don't have any question, please mute yourself so that we don't have interference. So the graph one. So the problem pi is asking you that, if I give you some graph, let's say I give you this graph, and I ask you, can you color this graph? Find the minimum number of colors that I can color this graph. Okay, that is a problem that somebody is giving you. And then suppose that there is another algorithm that says that given g and k is some integer, and this graph, this problem gamma would answer you if can g be colored with less than equal to k colors. Okay, so we already have an algorithm that can answer you that question. And then we want to find an algorithm that would help us to answer that. So let's basically color this graph. So the first question is that, can we color this one with 4 colors because I have 4 angles? Let's say I call this one blue. Then let's say this one is red. And this one is green. And this one is purple, right? So it look like that I can color this one with 4 colors. Let's see how do we actually want to use this idea. So again, I give you this graph and I say that can you color it with 3 colors. So again, I can go ahead and say, okay, blue here, and then I keep red here, and then I keep green here. So since we said 3 colors, so here I can put green because green would be adjacent to this other green. I can put blue because blue would be adjacent to this blue, but red is okay. So we don't have 2 vertices that connect. We don't have 2 vertices that are connected with the edge and they have the same color, so we are fine. Okay, so let's continue. 3 is also fine. How about 2? Can I answer this one with 2? So with 2 means this one would be blue. And then I already know that this 2 could be red. I have no problem. But can I put red here or blue? None of them, right? It's not possible. So then I would stop here and say that, okay, no, it is not possible. So look like 3 is the minimum number of colors that I can color this graph. So did you see that now we just solved that problem? We were looking for the minimum numbers, and then we use another algorithm that would actually try to color them with the number of the color that we gave, and it could either succeed or fail. So now we go to solve this with our algorithm, so with the reduction. So the reduction says that I'm reducing the graph coloring, the number of the minimum number of the colors that I need to color the graph, and I'm reducing it to gamma. Is this algorithm would literally go ahead and try to color with as many colors we provided. And then we would start with the number of the vertices minus 1. So in the beginning, I would send maybe this one with 4, and it says yes. So we continue, and then with 3, and then it says yes, and then we continue with 2, and then it says no, right? And then we go back and take the one, actually here I should say the algorithm says yes. The algorithm says yes. And then when I fail, I get no. Then I go back and maybe I should even make it more clear. No. And I go back and I take the previous number, and it looked like that the minimum number of the colors that we can use to color this graph is just 3. So I really hope that this notation of reduction is now familiar for you guys. We are going to use this reduction a lot. So I think we have covered multiple examples up to here, some that are successful and we can do in polynomial time. And one of them, we show that we can do it in a polynomial time. And that has a special meaning for us because we are showing that one problem is not actually solvable in polynomial time. So actually we can show it. So this would lead us to proof of security. Let me see if we have time for this. Yeah. So to prove the security of a crypto system lambda, let's say RSA is lambda. And then we define pi to be the problem of we find a hard problem, and then the point is to reduce these 2 guys to each other. So let's say let's plan this out to see how it works. I think the text would be hard. So suppose I have a problem pi, which is factorization. On input n, I expect to get p and q. Okay, but we know that it is a hard problem to solve. Okay, there's no problem. So we have a reduction to breaking RSA. Okay. So suppose that we pass this as f function, that we pass it to breaking RSA problem, and then there is the algorithm A that would claim that it would break the RSA, and then we would have to function G that would convert that sort of output or breaking RSA. We use that information to pass it to G so that we can compute P and Q. We are not trying to make this reduction here. We are just trying to show the relationship that what we would get. If we can do so, if we can really relate these problems, and we are also showing that this relation is polynomial time. So we have T1 here, we have T2 here, we have T3 here, right? And such that T1 plus T2 plus T3 is a polynomial time algorithm. So with showing this, we are saying that if somebody claims that I found an algorithm A that can break RSA in a polynomial time, then, what does that mean here? It means that if we use this guy, we set up an RSA crypto system with this N, we pass this N, and we let this algorithm A to break that crypto system, then with the result of that crypto system, we can actually find P and Q. But we know that by default, we know that factorization is a hard problem, is a hard assumption. We do not have any polynomial time to solve it, right? But this reduction is saying that, oh, actually, we do have a polynomial time algorithm B that can solve this problem in a polynomial time. And that implies that as long as problem pi is a hard assumption, then this algorithm A cannot exist. This algorithm A that claims to be polynomial cannot exist. Because if this algorithm A exists, then it means that we find a polynomial time algorithm for factoring any integer n. But we know that this is a hard assumption. This side we know. So we can conclude that it's not possible to have some algorithm like A over here to break the RSA. So that is how we literally show, RSA is a secure crypto system, because we are connecting these two problems. If somebody breaks the RSA, if we are able to write down the details of this, construction, and also A, and then we assume that A can be solved in a polynomial time, it means that we can solve factorization. So therefore, since we know that factorization is not polynomial time solvable, then it means that this algorithm A of breaking RSA in polynomial time cannot exist. And therefore, RSA is a secure crypto system. So this is the logic that throughout this semester, you are going to more or less work with it. I think this is the text of just what I said. I just left the text here for you to really understand. So let's go through it very quickly. So I just brought it here so that for those that they wanted to read it more concretely. So we are reducing the hard problem pi, which was factorization, to the security problem of breaking RSA, gamma. So we assume that there is a polynomial algorithm A that breaks the RSA algorithm. And this implies that RSA or lambda is not secure under the specified, security model. Okay. And then we design a polynomial algorithm B, which is that entire, reduction. After we design this B, which uses A as a subroutine to solve the, hard problem pi. And now we go back to the back routine. So we said that pi is assumed to be hard problem. So B of solving pi does not exist. Therefore, A cannot exist, right? That implies that as long as pi is a hard assumption, pi or factorization remains hard, P is secure under the defined security model, right? So we are just using sort of contradiction over here, but combining it with reduction, we can show that such adversary that claims that can break the RSA cannot exist because the moment this adversary says that somebody claims that I can break RSA with any key, then it means that we can solve the factorization. And as what I said, that as long as factorization and previous problem that we wrote the code, as long as factorization remains hard, that for loop, we don't find a better way to solve factorization than that for loop, then RSAs would remain secure because we can also prove the other way around, and we basically connect these two problems to each other. All right, I think this is enough.
Sorry, I've been lost for a while, but I didn't want to interrupt. Can you go back?
Here?
There. So I got a little bit lost because I know the B algorithm here. We're trying to find the thing that confuses me is that B and A seem to be doing the same, not the same thing, but they're the same problem because we define B as a way to break a RSA, which is also what we define A was trying to do, which confuses me because we're saying the same thing twice.
I see. So now A is an adversary that can break the RSA. B, we constructed with this green box after the interacting with the adversary or attacker. B solves the problem pi, which is factorization. Okay.
But
so
isn't breaking RSA trying to solve factorization as well?
So the point is, factorization is one of the ways to break the RSA. Let me go back. Remember, we suggested two methods, right? Method number one, that the adversary doesn't have to really factor in. She can just go ahead and try different Ds and see which one would satisfy this problem, right? So that is one way to break it. This is the method number two that involve in factorization. And there would be even more different methods to break the RSA. So breaking the RSA, it doesn't mean that you have to do factorization. There is at least another method that you can break the RSA. But as long as, that's what we are saying here, as long as there is an algorithm that can break RSA with any other method that we don't know, or adversary can come up with something that we've never heard of it before. If somebody that we call it A, some algorithm A can break the RSA, then we can use this B, which would just take N, feed it into the RSA, wait for the attacker A to break that RSA with that number N as a public key. And once this attacker breaks the RSA, we get those results, and then we use the function G to compute P and Q. So we don't know how A would break the RSA, but we know that if somebody claimed that they can break the RSA, we can find the D or secret key or whatever, then we can use that piece of information to compute P and Q. So this is the entire different thing is B here, that B would wait and make this interaction between these two algorithms and use that function F and G to compute the problem pi that we didn't know how to solve before. Okay, we know that, right? Somebody can break the RSA, with that method number one that try many different secret keys, but the problem with that is that is not a polynomial. The T2 is not polynomial. Okay, so we really need somebody to break RSA in a polynomial time, so that it really means that you have a really good advantage, some attacker that can break that problem. As long as we have that, and it doesn't have to be necessarily using factorization, they can use a different technique. As long as they break it, then we can use that information to solve our factorization.
Yes.
Okay? So, throughout the course, I don't want to go through the very details over here, but if you just wait a bit, we get to the public key, we would do construct this together, and then you will see that, you know, how we can utilize the information to compute P and Q.
Yeah. What I got lost as well is when you said that the part where we established the negation, like, it's just because we haven't found an A algorithm that we can affirm that B is secure. That's the part that I don't understand. It's just because we haven't thought about it, then we just say, oh, we can't.
Right. So, well, the point is, somebody's claiming, let's say I walk in and I tell you that I can break RSA in a polynomial time, which means that I have this algorithm A. Okay. If I make that claim, we know that T1 and T3 are polynomial, and I'm claiming that T2 is also A is also a polynomial. So that means that if you use this reduction with the details that we haven't specified yet, then your B, which is the problem, the algorithm for solving factorization, can also be computed in a polynomial time. Okay. Right. So,
and that's not true.
Yeah, and if we reverse it, I can say that as long as B cannot be polynomially time computable, that means that given this reduction, T1 is polynomial, T3 is polynomial, so it means that T2 is not polynomial, right? The only way that B can be non-polynomial. So that means that A that claims to be a polynomial time algorithm that can break the RSA cannot exist. Right? So I'm just changing my words.
Thank you.
All right. Any other questions? Okay. If not, let me see, what time is it? I think we took some of your break time. So let's come back. It is 9:56, and let's come back at 10:06 to continue the class.